So shall I begin? Yeah, it's my turn now.
Yes.
Yeah. So I am grateful for the invitation to do this seminar in Mexico, and I definitely wish to entertain you for about 45 minutes, and I hope that you dare to ask questions. So interrupt me if there is anything which you want to be clarified. So my topic today is an overview of the latest developments, let's say over the past 5 years actually, of core collapse supernova theory successes, and at the end I will talk a little bit about what the current perspectives are. This is an overview of the contents of the talk, where I actually dropped two of my favorite points, I must confess, because that's where I have spent quite a lot of work on over the past couple of years. And I will instead give you the introduction and the background and a little bit of this fundamental question, how supernovae explode and what is the recipe to make these stars exploding nowadays. And I think the problem of the mechanism of the explosion of the large majority of core collapse supernovae is solved by now. So we have frontiers where we now have to continue beyond that. And actually I've started that already a couple of years ago with a big funding which I had from the European Union. So introduction and background, then I will report the status of the 3D simulations, mainly with respect to what the neutrino-driven mechanism is providing. And I will give you the recipe which we now need to use in order to make the stars exploding in 3D. That we have to take into account the perturbations which exist already in the progenitor stars prior to their core collapse. And finally, as I said, I will review a couple of questions and perspectives. This is a slide which is adopted and adapted both from Adam Burrows' review in 1990, where you see how the evolution of a massive star from, let's say, in this case, a 15 solar mass star at the end of its life, 15 million years, roughly 10 to 20 million years. And this star has developed a degenerate core. This degenerate core is supported by electron pressure. It's here shown in an enlargement and has about the size of the moon. And these electrons provide stabilization against the gravitational force, which tries to contract this iron core. And roughly at the mass limit of the Chandrasekhar mass, not exactly, it can vary quite a lot, but roughly at the Chandrasekhar mass, this core becomes unstable. The initiation is by two different ways. On the one hand, it's electron captures on protons. The protons are mostly bound in heavy nuclei, initially at least, and the photodisintegration of the iron group nuclei into alpha particles, mainly at the beginning. And then this core starts to become unstable, gravitationally contracts, and within less than a second, it dynamically collapses to a neutron star. A shock front is launched, at least if the supernova is successful, explodes the overlying stellar material, ejects all of the mass except of this neutron star, which forms at the center. And you see an enlargement here. It's initially very extended, radius about 50 to 100 kilometers at the very beginning. It's hot, it's radiating neutrinos, it's receiving further mass from infalling stellar material. And then within about a second, it already contracts significantly. And within about, let's say, another 10 seconds or so, it cools off to the final neutrino transparent state, at which then this long time cooling, first by neutrinos and then by photons, starts. And that's a situation, or that's the conditions, or the whole scenario which we need to investigate by numerical simulations in order to get the answer what the type of processes are which lead to the explosion of the star, to the supernova. Neutrinos play a crucial role, as I already mentioned. They actually carry away the binding energy of this newborn neutron star, which is of the order of several 10 to the 53 ergs, or several 10 to the 46 joule. And this gravitational binding energy, 1% of this gravitational binding energy is tapped also by neutrinos to be deposited around the neutron star and then to drive the explosion. So 1% of this binding energy is sufficient to make the star explode. And again, from this kinetic energy of the explosion, another 1% is only used for this bright display, which supernovae are. You see these supernovae at cosmological distances, actually in distant galaxies, and you see them appearing with a brightness of nearly the nucleus of these galaxies. So this optical display is a very, very tiny amount of the total energy released and mostly carried away by neutrinos. This is one of, rather maybe the most famous example, happened 33 years or 4 years now ago in the Large Magellanic Clouds, or a neighbor galaxy of the Milky Way. And this was the very first case where we knew the progenitor stars, Anduliak, with this phone number here, -69202. And this star was a blue supergiant, astonishing at that time. Now we have more supernovae, which had a blue supergiant as a progenitor. And here you see the supernova on the right-hand side exploded on February 23rd, 1987. This is the neutrino measurement, which was the first measurement of extragalactic neutrinos. Now we have a second measurement, as you know, from active galactic nuclei, these ultra-high energy neutrinos. Otherwise, we have neutrinos only from the sun as a cosmic source. Of course, we have the high energy neutrinos from the interaction of cosmic rays with the atmosphere, but direct neutrino measurements are very rare. And this supernova provided about 24 neutrinos in 3 detectors at that time. And this signal was compatible with the predictions with respect to the individual energies of the neutrinos, with respect to the duration of the signal, and also the total energy which caused these neutrino events in the detector. These were electron antineutrinos, so we measured only a fraction of the of the neutrinos released, because all types of neutrinos carry away the energy from the newborn neutron star. The problems and the questions in this field are very diverse, and for that reason, supernova research is actually going in many different directions. So we don't want to understand not only the explosion mechanism of the supernovae, we also want to, of course, determine by theoretical models the explosion properties, asymmetries, the properties of the newborn supernova remnants, the gas which is ejected into interstellar space. We want to determine neutron star and black hole formation, paths and probabilities, and the properties of these objects. Now black hole formation is actually in the focus of interest because of the gravitational wave measurements, which are mostly connected to binary black hole mergers. We also want to understand and predict neutrino and gravitational wave signals, although only measurable if we have the lucky event of a galactic supernova. A lot of observatories around the globe get prepared for this measurement. Then we have physics interest in supernovae as a laboratory where neutrino flavor oscillations could play a role. Non-standard physics could play a role and may also be measurable if we had supernova neutrinos in the future. For example, sterile neutrinos, but also a lot of exotic scenarios connected to dark matter predictions or dark matter possibilities. Heavy element formation, not necessarily nowadays anymore and any longer connected to the question where the R process comes from. We think that the main site of R process formation may be neutron star mergers, but there could be exotic supernovae, very rare supernovae, which could contribute, in particular in the early universe. And then finally, nuclear physics connected to the equation of state, maybe ultra dense matter, quark phase transitions. Also, those can be studied in the case of a supernova from which we can measure the neutrinos. Let me now come to more and more details stepwise. I start with cartoons, with images first to give you the basics, and then I will show you the real situation in numerical simulations. So this is again this initial condition where we have what is called the onion shell structure of an evolved massive star, more massive than about 8 solar masses. And at the center, this iron core has been formed by this succession of nuclear burning phases. And this iron core is surrounded by shells of ashes from the previous burning stages. And we will, in the following slides, focus on this inner region here marked by this red square. And I have zoomed it here on this slide. and already superimpose something which will become very relevant during the later parts of my talk, namely that these shells are actually not spherically symmetric. They are perturbed. Also, the silicon shell would have to be perturbed, but we don't know yet exactly how that looks. This is here what you see in the oxygen shell. Here, oxygen is marked, is the result of a real three-dimensional simulation, which I will show later in my talk. So at the onset of collapse, the iron core initially contracts relatively slowly because of the photodisintegration setting in when temperature is high enough. And then this will accelerate, and actually within less than a fraction of a second, a neutron star will be formed, which we call proto-neutron star, this first condensation core of what will be the later neutron star. And at this event of core bounds, when the nuclear phase is reached, the phase transition sets in, the equation of state stiffens, and this neutron star, condensation core of a neutron star bounces back and sends out a shock wave into this still infalling outer material. At the beginning, it's the iron core material. Later, it's also the silicon shell, and then the oxygen shell will follow. But it was already known from the first sophisticated and detailed simulations in the 1970s that this shock wave doesn't make its way out of the neutron star. There was still hope until maybe the year 2000, when people then started to do very, very detailed 1D modeling. There was still hope that this shockwave at some point, when one does the physics right and most detailed, will make its way out of the iron core. But in fact, we know from the latest simulations also that this shockwave loses too much energy in photodisintegrating iron into neutrons and protons. And therefore, the shockwave stalls, it stagnates, and it doesn't continue to the edge of the iron core, but has to wait for the material falling further in, and then feeding actually more and more mass onto this neutron star. So the neutron star is growing during this period of time. What's happening is that the neutron star is radiating more and more neutrinos. It's heating while it's contracting, and so the neutrino luminosity stays high. And at the same time, the mean energies of these neutrinos is growing steadily during this time. So the neutrinos become hotter and hotter, or harder and harder in their spectra. And this at some point then allows the neutrinos to deposit enough energy in this layer below the shock wave, so between the neutron star surface and the shock wave. And this energy deposition the neutrinos are doing there is mostly taking place by neutrino absorption on free neutrons and protons. And if this absorption is effective enough, if it's efficiently depositing energy, then it pushes the shock further out. I've tried to actually sketch that the shock is deformed. At that time, my abilities to use these graphics tools is not good enough to do it more in a more realistic way. But maybe from this deformation of the shock, you already can conclude that this shock wave is revived asymmetrically because of what is going on behind the shock wave: neutrino energy deposition and hydrodynamical instabilities. Well, you can coin it in very simple words and say turbulence. People like to use this term because turbulence is fashionable. It happens in many fields of physics and people accept it easily, but actually these hydrodynamical instabilities are a bit more complicated. I will get back to this later. That's on the one hand convective overturn, and on the other hand a SASI, instability called SASI. And these instabilities deform the shock wave and push the shock due to this energy deposition, which delivers the energy for the explosion. They push the shock out against this still infalling outer stellar material. And behind the shock wave, then there will be nuclear synthesis. Nuclear synthesis will form nickel. Nickel will also be formed in this neutrino heated material. And the nuclear synthesis will then lead to the radioactive elements, which make the supernova bright actually over months, if not years. If the supernova is not too distant, we can actually observe its bright electromagnetic radiation, mostly powered by a radioactive decay of nickel. We can see that over years. And this is the next stage where the neutron star is left behind. And in some of these events, we get what is called a neutrino-driven wind. So the neutron star is still radiating neutrinos, and neutrinos deposit still energy in the surface layer of the neutron star. And this will push a wind, which then pushes these asymmetries further out. This wind doesn't happen in all cases. It happens in low mass stars. In more massive stars, we have actually ongoing turbulent mass flows around the neutron star for periods of seconds. There is actually never a never-ending phase of infall of material and then ongoing neutrino heating. And then later, when the neutrino heating is too weak, there will be mass fall back for some period of time towards the neutron star. So the shockwave is launched, the shockwave goes out through the whole star, and before the shockwave reaches the surface of the star, it takes the shockwave maybe hours, depending on the radius of the star. It takes hours for the shockwave to propagate through these millions of kilometers wide star. The neutrino heating mechanism actually in its principles, in its basics, is known since the 1980s. The first work was actually by Jim Wilson through numerical simulations, and Wilson together with Hans Bethe have done the detailed calculation of the neutrino heating energy deposition by neutrinos. The idea is even older. The idea goes back to Colgate and White, who had actually put in this heating by neutrinos in their first 1D simulations in the 1960s, of course, completely artificially and not really realistic with respect to the numerical values. That has actually then been done in a paper by Bethe and Wilson in 1985. And I have summarized the essence. So you have a neutrino luminosity from the neutron star. You have a certain neutrino spectral temperature. I focus on the electron neutrinos here, but the electron antineutrinos are added in this factor. Here you see the absorption of electron neutrinos on neutrons and protons is taken into account in the scaling relation here. So it's both these reactions which play a role. And this scales here with these factors, luminosity to the power of unity, and then the temperature of the neutrino spectrum, which of course scales with the mean energy of the neutrino spectrum to the square. And then there's this a factor of 1 over r square, which is just this light bulk dilution of a neutrino source with a certain radius, neutron star radius. And then you go away from the neutron star, and then this dilutes with 1 over r square roughly. And this is a cooling term, which also means that these reactions in the opposite direction play a role. Electron captures on free neutrons and positrons, of course, but they scale here with a medium temperature, with a gas temperature. Electrons and positrons are in a thermal equilibrium path, and this is the factor. But you see here, the temperature enters to the 6th power. And one now needs to know, which I have not written on this slide, that the temperature outside of the neutron star declines roughly like 1 over r. So this factor here, scaling with the temperature to the 6th power, drops like 1 over the radius to the 6th power. So much, much steeper than its heating term. And Bethe and Wilson already understood that at some point, which we call gain radius, heating will become more relevant than cooling. And that's the region where the neutrinos then deposit the energy. And that then you can estimate from this energy deposition rate per gram and second, multiplying with a typical mass in the gain radius, in the gain layer. I have here taken about 100th of a solar mass. You can see that this is a huge amount of energy which can be deposited of the order of about 10 to the 52 ergs per second. So 10 times more energy than needed for the explosion can be deposited per second. So in other words, the energy deposition over fractions of a second would and should be able to launch the explosion. You can, well, then calculate the typical time scale over which material can be heated, which is now from the numerical simulations, the mass in the gain layer and the mass infall rate, which is typically in a steady state. So it is the same mass infall rate ahead of the shock as mass falls onto the neutron star in the steady state situation of the stagnant shock. And then you find that this stagnation time is typically of the order of, or this heating time, dwell time of the material in the gain layer is typically of the order of a fraction of a second, or maybe even less than 100 milliseconds. And this is the problem in 1D simulations. In 1D simulations, you don't heat long enough. You have to go to multidimensional simulations in order to increase, due to this turbulent mass motions, to increase this dwell time. As Boros and Goshi already recognized in the early 1990s, I did that at that time with numerical simulations. Boros did it in analytic ways with steady state assumptions. This is a critical phenomenon. So we have a critical curve, a boundary curve, where the mass accretion rate is competing with a neutrino luminosity. Evolution of the stars is in this direction towards decreasing mass accretion rates. And when the conditions cross this critical luminosity curve called the critical luminosity as a function of this mass accretion rate, then here these white blobs indicate successful explosions. If the conditions in the collapsing star stay in the upper region, no explosions happen. And in order to determine whether the stars cross this boundary line of the critical curve, again, numerical simulations are needed. We need self-consistent simulations, and we need to do these simulations actually in 3 dimensions. The reason I will mention in a couple of minutes or in a couple of seconds. There's a lot of input needed for these dynamical models, which we do on supercomputers. We need the hydrodynamical solver or magnetohydrodynamics, even for the stellar plasma. We need to take into account general relativity, nuclear physics, neutrino physics, and neutrino transport. And of course, we need to start with initial conditions, the conditions coming from progenitor evolution. All that enters these models, and then running the simulations long enough, we can predict neutrino signals, gravitational wave signals, explosion energies, the remnant masses, light curve and spectra, asymmetries of the ejecta, pulsar kicks, nucleosynthesis. And that's all what we work on when we do theory in the supernova sector. So it's a very diverse field of theoretical research. This is a subset of the equations which we need to solve, just showing you the complexity. And these are only the equations in 2 dimensions. So that's the 2-dimensional version of the relativistic hydrodynamic equations, solving mass conservation, energy conservation, momentum conservation, conservation of the nuclear species or the electron fraction. We evolve all these equations. Then we need to couple them with some kind of a metric solver for the Einstein equations. This is here a certain approximation, which is called conformal flat condition. We did that and do that in the coconut code. In other codes, we do it even more approximately. There's even new codes where we do it in full-scale general relativity. But these codes are very time-consuming and have more small time stepping because of the gravitational waves, which are online simulated with the numerical simulations. And one of the major complexities of all this game is with the neutrino transport. This is just the 2-moment equations. What we solve is also some version of the Boltzmann equation to get a closure for these equations. So that's a really complicated task, which can only be done, again, on supercomputers. There's a lot of physics input in the neutrino sector, neutrino reactions, the ones which I had shown you, which are called beta processes, but also neutrino scattering, thermal processes. And what I do not list on this slide, what we have newly implemented only for a couple of years now, 3 years, is neutrino interactions with muons, which we also take into account, not just the electrons as leptons in this medium. And that's the reason, one of the reasons why we have to go to 3 dimensions, and 2-dimensional results are never reliable with respect to their quantitative output. Qualitatively, yes, we have learned a lot doing 2-dimensional simulations, but quantitatively, 2-dimensional simulations are not reliable and not meaningful. So this is the two-dimensional simulation mapped into the 3-dimensional space, and you see that all structures you see in 2 dimensions are actually tori. And what the big problem is that in 2 dimensions, the turbulent cascade pumps energy from small scales, from the small scale turbulent scales into the biggest scales. And that's the reason why in 2D, one always sees the biggest scales growing fastest. And in 3D, it's the opposite. We have fragmentation of large scale structures into small scale turbulence. And this means a completely different consequence in the 3-dimensional simulations of supernovae. The largest scales push the shock most efficiently. The small scales create turbulence, but turbulence is not so efficient pushing the shock wave. And therefore, 3-dimensional simulations provide explosions much harder than 2-dimensional simulations. The big breakthrough for us came at about 2013, when we could for the first time access massively parallel supercomputers in Europe. The first supercomputer we used was this machine here in Paris, which is called Curie. It doesn't exist anymore. Half-life of these supercomputers is a few years. At that time, we got this through a newly founded initiative for supercomputing, the PRACE initiative in Europe. So we were very lucky getting a lot of computer time in the first 2 years from this machine. Then later we could also use Mare Nostrum in Barcelona, and and afterwards from 2015 on about, we could use this big SuperMUC in our neighborhood here in the Leibniz Supercomputer Center in Garching, and this machine now has a successor machine, even bigger, SuperMUC NG new generation. So at that time we were really lucky. Now it's much harder to get computer time because we don't fight only the cosmologists with respect to our competition for computer time, but also the gravitational wave community. And we have in Europe quite a number of groups doing gravitational wave simulations, neutron star merger simulations, and they need a lot of computer time as well. And we now have a really hard time to get enough computing resources on these machines for our supernova research. Supernovae are not fashionable at the moment. We need another event which is observed nearby, where we then can detect neutrinos and maybe even gravitational waves. Now let me come to numerical simulations, and I can only flash the basics and the most relevant steps which we have done in Garching, and at the end I will summarize and tell you what other groups have also achieved. The big problem is the diversity of these stars, and here in the upper right corner you see a plot where I show these density profiles before the star begins to collapse, just at the onset of collapse, and you see that there's a huge diversity. Low mass stars like this 8.8 solar mass star, which has actually no iron core, it has an oxygen near magnesium core, but still collapses. This has a very steep density profile. And then when you go to typically more massive stars, you see that the density profile gets shallower, and more mass is actually sitting outside of this iron core or of this degenerate core with high densities. And that actually, between some 10 or 12 solar masses and 15 solar masses, makes it very hard to explode stars. But for more massive stars, then it can become a bit easier, because this high mass infall rate doesn't only prevent the shock expansion, it also actually creates neutrino emission. So there's a competition. Yeah, I don't go into the details now. The rest of the information on this slide is not so relevant, but this density versus radius plot is relevant, because I will go now through a couple of cases which we simulated over the years. Now let's start with this the lightest stars, the low mass end of the range of progenitor stars. I talk here about stars with about 9 solar masses, somewhere between 8 point something and 10 solar masses. And for those cases, for some of those cases, one actually can also obtain explosions in spherical symmetry. This here is one of the cases which we ran already back in 2006, 5-6, with a student of mine, where we found an exploding condition in a spherically symmetric simulation. So this here shows a mass shell diagram. I will show several of them, where you have the initial radius here, a logarithmic scale. On the right axis, we have the time, and you see that these mass shells start collapsing. So this is the stellar collapse. Within less than a second, this collapses to the newborn neutrons, to the conclusion of a newly formed neutron star here down in the lower part of the diagram, where you see these mass shells then contracting over time, and that is where the neutron star forms here at radii of some 10 kilometers. And then you see at the moment of core bounce, the shock being launched. The shock here in this case is moving out very rapidly, and that creates favorable conditions for neutrino heating. And therefore this star, because of this outward running shock, this star explodes fairly easily. This can also be simulated in 2 dimensions, and then you see that there is some asymmetry starting. These kind of mushrooms are what is called Rayleigh-Taylor instabilities. They provide some mixing in this post-shock region, but they are in this case not crucial for the explosion. These mushrooms you actually also know from experiments in the atmosphere of the Earth. When you explode a nuclear device, for example, or a very energetic bomb, then you see a mushroom rising because of this high entropy material produced by the energy release of this nuclear device. And these mushrooms in the Earth atmosphere can actually rise even 10 or more than 10 kilometers. In the case of a hydrogen bomb explosion, for example, the mushroom is extremely hot and rises into the upper atmosphere. And these are the mushrooms of the same nature which we see here in this supernova simulation. In 3D, this looks like that. So we have many of these mushrooms and they push the shock, but they are not crucial for these low mass explosions. Interesting, these low mass explosions are of the order of about in energy 10 to the 50 erg, so about 10% of the typical supernova, or 20% of a typical supernova explosion energy, and they create very little nickel. So they are connected to relatively dim, faint supernovae, and we have one case in our neighborhood, Crab, which has been thought to be connected with such type of explosion. Here it's an image of a crab. We don't know whether it's an explosion of an oxygen magnesium core case or such an iron core explosion. It's a low mass iron core explosion, which I show you here, 9.6 solar mass star. And let's run this movie to give you an impression. So what does the movie show? This movie is an entropy, isoentropy surface. The shock is visible here as this bluish enveloping surface. And you will see that the shock runs out extremely fast, but nevertheless, this material here develops some asymmetries because of the convection I have shown before on my slide. So let's run the movie. There's the time here in the top right corner. Now you see this convection growing, these mushrooms. These are due to neutrino heating around the neutron star. And these mushrooms grow. Here they fragment, they create some turbulence. The shock is already gone. The scale of this size of the window is on the bottom part, and you see that this now in a diameter about 3,000 kilometers, and it's expanding very rapidly for those low mass explosions. Okay, so this is an explosion of a 9.6 solar mass star with an iron core, and it was relatively easy, and we obtained it in 2015 already in our very first attempt to get 3D explosions. But we had a problem with more massive stars, and these more massive stars show a lot more dependence on these instabilities, which I had mentioned before. That's on the one hand convective overturn in this post-shock region between the neutron star and the shock. The red band here marks the region where neutrinos deposit energy by these reactions, which I had mentioned. And here not only convection occurs, but also what is termed SASI instability, the standing accretion shock instability, which is a large-scale instability and leads to a large-scale deformation of the shock wave. One can actually do experiments in the laboratory, and my friend and colleague in Paris has actually built that in the garden, in his own garden. Now it's in a laboratory. It's a hydrodynamics experiment where you feed in spherically, or let me say radially symmetrically, you feed in material, water from the edge of this table, and then the water is flowing down a curved surface and is meeting a pipe and flowing out. And this pipe here absorbing the water is the neutron star in the supernova context, which accretes this infalling material. And when you actually increase this inflow rate of water, then there is a stall of the water, and there is a water jump formed, which is called hydraulic jump. And this hydraulic jump is very similar in its behavior to the shock wave instability, which we have named SASI. You will see this in this movie. Let me play the movie. And this movie actually shows a sloshing of this hydraulic jump, which you will see in the next movies I will play for the supernova case. And this is the pipe here receiving the water. You hear the water noise. And this is a rotating case. Not the plate or the table was rotating, but what was rotating here is this instability, and that was triggered by some asymmetries in this flow. So these are the instabilities which we also see in the post-shock region, and I show you our first successful case, which was prominently pushed by this instability in 3 dimensions. This is a rotating star, and I will play a similar movie to the one you had seen before. Now again, you see this rotation here. You see that there is kind of a convection starting first, but then this standing accretion shock instability takes over. It deforms the shock massively in a low mode asymmetry, a dipole asymmetry actually, and pushes an equatorial explosion in this rotating model. So the rotation axis is perpendicular, and you see the explosion being pushed towards the equator because of this asymmetry created and this standing accretion shock asymmetry pushing the shock further out, and then again creating favorable conditions for the energy input by neutrinos. All this is done with full-scale neutrino transport. We simulate really here for tens of millions of core hours to get such an explosion on a supercomputer using 16,000 cores in parallel over months, continuously over months. This is
I have a, so what I didn't understand is, was SASE needed in the 9.6 progenitor, or
no?
Or
no, actually, no, it was not needed. And actually the 9.6 solar mass progenitor, whose shock expansion you can see here on this slide, this is from the 9.6 solar mass model. You see that the shock is continuously expanding. And when you have a continuous shock expansion, you don't get favorable conditions for this SASE, because the SASE instability is what is called an advective acoustic instability. It requires mass inflow towards the accretor, and the more massive this mass inflow is, and the smaller the radius of this stalled shock wave, and here the hydraulic jump is, the more violent this instability can become. The growth conditions, you can do that analytically. Actually, we have published papers already in 2008 and 9, where we did these estimates analytically, that the SASE instability the SASE instability grows most favorably when the shock wave is receding. And you can see this recession of the shock wave here in the 20 solar mass simulation, which I show you in a minute. And also there is a recession or a stagnation of the shock wave in this red case, with this, which is the 15 solar mass model.
Okay.
Yeah.
Thank you. Yeah, great.
You're welcome. So this is now the case I mentioned, the 20 solar mass model, which we also published already in 2015. And this model, in our first attempt, which we already started on the supercomputer in 2013, we failed to explode this model. So something was missing. And the something was, as we guessed at that time, might be connected to the neutrino sector, because describing the neutrino matter interactions is a very, very complicated business. So what we added at that time was a very, very small correction to a subset of these complex neutrino reactions. What we did was we added what is called the strangeness correction, a strangeness contribution to the neutrino connected to the nucleon spin, to the neutrino nucleon scattering rates, to the neutrino neutron and neutrino proton scattering rates. And this actually changed the neutrino nucleon scattering rates for the relevant neutrino energies on the order of something like 15%. And this was only these two reactions, neutrino scattering on neutrons and protons. And that was the only change we made. And this change then led to an explosion. This was criticized later on, because we used this factor here, this correction factor GAS for the spin correction. We used a number which was a bit larger than what was compatible with the experiments. We used -0.2, while the experiments at that time said the favorable number is about around -0.1, but the error bars were in the maximum at -0.2. So we maximized the effect, used -0.2, but some people complained that this is not a realistic effect in supernova cores. It was not meant to be realistic at that time. It was meant to be one possibility in a way which is not unphysical, to show the large or enormous sensitivity to the details of the neutrino physics. And as I told you, this model at that time produced an explosion, and I show you the movie here, and you will see SASE occurring in this simulation very prominently as well. So this is the bouncing now. This is what you had seen in the SASE moving. This is a sloshing SASE. So we see it, and now you see the spiral SASE setting, and we rotate the model. This is just an artificial rotation to demonstrate the asymmetry. And this is, we stop rotation. This is now again SASE, and now when the shock is already starting expansion, we see convection taking over. These are the mushroom plumes which I had talked about, which then continue to push the shock. But the initiation of this shock expansion was connected to the SASE. And now you see the shock moving out, and the shock is highly deformed, and now we launch an explosion. An explosion is launched in this 20 solar mass model. Because of this slight and tiny modification in the neutrino sector, the failed model was turned into a successful one. Okay, this was not the solution of the problem. We knew that. This was a demonstration. What turned out afterwards to be really a crucial input for further successes later on, And all the models published in the literature right now, unless these models invoke unrealistically fast rotation, all these models, if the people tell you or if they hide it and don't tell you, all these models are based on adding three-dimensional asymmetries from the progenitor, not created only in the phase of core collapse, but already present in the progenitor star. The problem was and still is that all these progenitor models, the initial conditions we start our simulations with, all these progenitor conditions are created by stellar evolution modeling. And as you know, stellar evolution modeling has to be done over millions of years, and that can only be done in 1D. But spherically symmetric initial conditions are not realistic. In order to create three-dimensional initial conditions, we had ourselves to go backwards in time. And that was done for the first time around 2015-16, when Bernhard Müller, a previous student of mine, and Maxime Vialet simulated in an 18 solar mass progenitor this three-dimensional oxygen shell convection for a period of about 5 minutes. And you can see that the oxygen shell gets massively perturbed. This is about 3 minutes after the start of this simulation. And this is the situation down here, about 5 minutes. So we went back 5 minutes and then simulated again from these -5 minutes to the onset of core collapse. And this is already massively perturbed the star at the onset of collapse. And indeed, this made the star then transition from a non-exploding simulation where the spherically symmetric initial conditions were used into a successful model. Bernhard Müller then demonstrated it, however, with a bit of simplification in the neutrino treatment. He found that this initial perturbation in the progenitor, which was actually fueling the post-shock instabilities. It was pushing harder on the post-shock instabilities. It was a seed for even stronger post-shock hydrodynamic instabilities. This helped the explosion. We have done that now more recently in the case of a 19 solar mass star, which is a very interesting star because that could be a progenitor of the type 87A had. And we have, in this case, an oxygen neon shell merger prior to core collapse. In this case, we went back 7 minutes and again simulated this star before it started to collapse. And I show you a movie here. The movie actually shows now a surface with a constant silicon fraction. So silicon is the burning product of oxygen. So what you see here is this product of oxygen burning with a constant mass fraction. And you see that over the next 7 minutes, there will be massive perturbations and asymmetries, which will be created by this convective oxygen burning, which can never be done in this way. Of course, in spherical symmetry, you don't see these asymmetries. Now, this is after a time of about 2 minutes, not quite two, sorry, this is already minus 100 seconds through core collapse. So this was about 3.5 minutes of simulation. And now this movie continues here in the top right corner. We measure the time up to collapse. And now you see this oxygen neon shell merger has happened and creates even larger and bigger asymmetries. And also this model we used more recently, actually over the past year only, we used that as input to three-dimensional core collapse simulations. My postdoc Robert Bollig was then running these models, and he found again an explosion only in the case where he started from the three-dimensional conditions in the progenitor. So the model which was started with the spherically symmetric initial conditions from the stellar evolution modelers did not explode. And we were for the first time then able to run this model for a very long period of time, namely out to 7 seconds after the bounce. And this was the very first model. Here you see the neutrino signal, which we computed in this simulation with highly sophisticated neutrino transport, neutrino luminosities. They actually have, we run the model until more or less the cooling of the neutron star is finished. 7 seconds here, convection in the neutron star accelerates this cooling very strongly. And here are the mean energies of the neutrinos. They already start to decline at the end because the neutron star is beginning to cool off. The model is highly asymmetrically. You see 3 snapshots after 500 milliseconds after bounce, after about 1.6 seconds, and this is after 7 seconds. So this shock is expanding highly asymmetrically. And for the first time ever, we could run the model long enough to see the saturation of the explosion energy. And in this case, it's 1 beta. So statements you can read in some papers from some colleagues that three-dimensional supernova explosions don't produce explosions which are energetic enough to be comparable with observations. This is certainly not true, but most of the three-dimensional simulations, or all other three-dimensional simulations which have been published by other groups, are stopped at a time of less than 1 second. This is actually not enough to determine the explosion energy. You see that when you stop at 1 second, you get about 0.3 beta in this case, but 0.3 times 10 to the 51 erg. You have to really run for a very long period of time to see this energy leveling off and reaching its final value. I can show you a movie here.
Thomas, can I ask a question?
Yeah, of course, you can.
Hi, this is William.
Yeah, no.
So the growth time of these instabilities, which you did multidimensionally in the progenitor,
yeah,
is much shorter than the timescale for that burning phase.
Yeah.
So how do you, I mean,
yes,
how do you know that it has reached the state, or that is?
Yes, the question is absolutely valid. It's absolutely valid. There is a lot of concerns about what we had done here. You are perfectly right. The burning phase of oxygen is maybe days or even longer, and we run for a couple of minutes. Our goal actually was and is to run maybe for hours, but we will certainly not be able to run this burning phase for the whole duration of oxygen burning. You're right. We find a kind of steady state at the end, but of course, what we have is still that this convection eats at the edges of the convective layer. Yes, I have to confess, I have to admit that this is a problem. That's all we can do. It's nothing we can add to that at the moment. We may, sorry, yeah. Some other people just put in these perturbations by hand. I think the Princeton group around Adam Boros just puts in perturbations by hand. This is even, let me say, more questionable. We do it to some extent consistently, but I know this is not the solution of the problem. But to be honest, I'm not sure when stellar evolution will be able to run three-dimensional simulations over periods of weeks or even months, or even if you are demanding over the full evolution of millions of years of the progenitor.
Yes, no, it's nice. Yeah? Thanks.
Sure, you're welcome. So let me quickly run the movie, which is now a bit different from before. We have not produced a three-dimensional movie of this simulation yet. So this is on the left-hand side. It's the one which is run from the three-dimensional initial condition. So you can see the perturbations here in the progenitor oxygen shell, actually. And on the right-hand side, you will see the simulation started from the spherically symmetric progenitor. And let me run it. And both of these frames show the time on the upper right corner. This right movie will stop at 700 milliseconds after bounce, but it will not explode, as you will see. And this one with the perturbations will develop the explosion, which I have mentioned. You see that this model with the perturbations develops much, much stronger post-shock instabilities. And in the end, we have to zoom out now because the shock is expanding and expanding and expanding. The movie stops at 1.5 seconds, but I showed you that we continued until 7 seconds. We have no full movie yet of this simulation. It's not so easy to produce these movies because the scales and everything changes so quickly. So it requires fine tuning, and my postdocs don't have time to produce movies. Okay, so this is our latest model. We have a paper on the server now in the revision. I have just finished writing the revision. The revision will be twice as long because the referee had so many questions that I had to add a lot of material into the revised paper. What's interesting is the nucleosynthesis. We run a small network in the simulations. We can determine the masses of certain elements, nucleosynthesis of radioactive species. And most interestingly, we actually find full compatibility of the electron fraction in these ejecta, or let me say the neutronization, or the neutron to proton ratio in the ejecta. We find full compatibility with nucleosynthetic constraints. The constraint is that there should not be more than 10 to the -4 solar masses of material ejected with electron fraction of less than 0.47. And you see that this ejecta mass here from the neutrino heated material fulfills this requirement perfectly. This is much, much smaller than this condition which these neutron-rich ejectors should fulfill. Otherwise, you would, if there were too much mass, you would overproduce material with a closed neutron shell mass around 50. Okay, Now, towards the end of my presentation, let me give a little bit of an overview what other groups have achieved. Now, this is the activities which we have done in Garching. I reported to you the models which are listed here. The latest one is the 19 solar mass model, which we have published only in the explosion case only very recently. Then there is Bernhard Müller now at Monash in Australia. He has a group there, or he's with Alex Heger in the group, and he has run his own models in 3D with a little bit of simplification on the neutrino sector. These are all published and successfully exploding three-dimensional models nowadays. There is the Oak Ridge group, which unfortunately has published only one model back in 2015 of a 15 solar mass explosion. There is the Tokyo Fukuoka group, who has become productive more recently. Again, I have not listed them. They had a model with very simple neutrino physics back in 2014. They have now more interest in rapidly rotating progenitors. And this is from the Caltech perimeter NCSU collaboration around Luke Roberts and Jean Couch, which has also a set of models. And Princeton very recently, from 2019 on, has started three-dimensional modeling, and they have a very efficient code. They produce a lot of models. They have also a huge amount of computer time I can only dream of. So they run many three-dimensional models nowadays, although they stop all their models at about 1 second. For the low mass stars, they can continue a bit longer, but the high mass stars are stopped at about 1 second only. The inputs to those simulations and also the quality of those results, however, differs a lot. I cannot really discuss the details here. A code comparison in 3D is missing, and some of the groups actually even haven't published the details of their numerical methods. This is a summary slide now, the status summarized of these three-dimensional modeling. So three-dimensional supernova models are successful. They have become mature. In 2D, there is a lot of differences compared to 3D. So you should not believe two-dimensional simulations in the quantitative details. Neutrino-driven explosions in 3D work for a large variety of progenitors, and now we even have achieved to run some models long enough to see the energy saturation for the final explosion energy. One of the problems I mentioned is that there is 1D progenitor data which are provided by all stellar evolution modelers, whether they are done with a Kepler code or now most recently with a MESA code. And these one-dimensional models don't explode when you use them directly in these simulations. You have to perturb them. The Princeton group is doing that. I know from the papers, they do that by hand. We have gone back a couple of minutes and run three-dimensional simulations. 3D simulations may still need somewhat higher resolution. There may be resolution dependencies, but for the perturbed three-dimensional models, we actually found that the resolution dependence is very modest. And always an issue to worry is, of course, uncertain or missing physics, in particular connected to the nuclear equation of state. I could talk a little bit about that, but I don't have time. And of course, neutrino physics in dense neutron star media, high temperature conditions is always something which we have to be a bit cautious to believe in all its details. We use the latest physics. We have some correlation effects for neutrino interactions with correlated nucleons based on random phase models. We have also effects due to weak magnetism corrections, nucleon recoil effects. We have the latest physics, but of course there may be developments in this sector in the future. And neutrino flavor oscillations are now a hot topic of exploration, in particular on the side of the particle and neutrino physicists. They are very much interested. They are very hard to discuss in detail. We don't know exactly how much they are relevant. We have some studies now which point out and point to the possibility of flavor oscillations happening. And this is now what is called fast flavor oscillations. They happen in the neutron star core or in the core surroundings, and they may also have some quantitative influence on the explosion. Observational consequences are very interesting. I have no time, so this is another talk. I have spent a lot of work over the past 5 years funded by this big grant from the European Union on exploring these consequences, also with respect to predicting neutron star kicks, predicting remnant properties, supernova remnant properties. I worked on 87A and Cassiopeia A. No time to report here. And this is again the list of open questions if you are interested in the question where the field actually is currently moving. thank you for your attention and thank you for the patience. I think I used about 5 minutes more. If I subtract the time for questions, I think I used about 5 minutes more than we had planned. Thank you.
Thank you very much, Thomas. We have questions, please, Felipe.
Hi, I am Felipe. I'm just
Hello.
starting studying Supernova in my PhD. So what do you think is the main difference between a core collapse? What's the main mechanism that makes a core collapse explode and a low mass star doesn't, you know, like they have a much smoother expansion? And
Yeah.
what do you think is the main mechanism?
When you say low mass star, you now mean the stars below about 10 solar masses. The
Yeah,
ones,
yeah.
Yeah. The reason there, I can tell you, I go back. That's the reason why I don't stop my screen sharing. I go back to those slides, which were connected to this topic. So here you see these density profiles. Yeah. Oops. Here you see the density profiles. And what is helpful is this extremely steep density gradient outside of the general core. For the 8.8 solar mass model, and because this model goes back to Ken Nomoto, a Japanese stellar evolution modeler, here is the degenerate core containing oxygen, neon, magnesium, and outside of this oxygen, neon, magnesium core, the density profile is extremely steep. Also for the 9.6 solar mass model, the second model I showed you with 3D results here, this one, the density decline is extremely steep. So these stars have a low mass infall rate on the newly formed neutron star. And for that reason, the shock can expand continuously. And that actually creates favorable conditions for the neutrino heating. The material here cools because of expansion, and then the energy deposition by the neutrinos leads to this deposition of energy, which is needed to create the positive energy output or the positive energy which is needed for a supernova explosion. The same phenomenon you can see here. The shock is never retreating. You see that the shock at some point starts expanding, and then the neutrino heating starts to become very efficient and pushes the shock further out. Actually, when we run this 9.6 solar mass model in 1D, we also get a very late explosion in 1D because of this decrease of the mass infall rate, which then allows the shock to move out. So what is helpful in these low mass stars is certainly that the shock is expanding. And that is also something which you see in Adam Borow's more massive progenitor simulations. In his case, he has a much easier time for getting explosions because the shock is always expanding. And if you ask me now why in his models the shock is expanding, while we see these contraction phases of the shock, I cannot tell you, because this is one of the subtleties. We see this contraction phase, which is actually not helpful for the explosion at all. Answering this would require to know what exactly he's using or the other groups are using in the simulation. In all of the other groups, this shock contraction phase is seen, while the Phonak simulations in the Princeton case does not show this, and in their models, the three-dimensional simulations explode much easier than our three-dimensional models.
Mm-hmm. Okay, thank you.
Sure, you're welcome. Thank you for the question.
Danny,
Anybody?
please.
Yeah.
Oh, hi, Thomas. Thank you very much for the talk. It was very interesting. I have one question. I'm interested in what kind of neutron star mass you would expect if you can get very low mass, like 1 solar mass. Because I remember I asked Chris Fryer maybe 10 years ago about the electron capture supernova.
Yes.
And he said, oh, I'm sure I would be able to produce like 0.9 or 0.8 solar mass neutron star.
Who said this?
That was Chris Fryer. He didn't say he had done it. He should be able to do it. So I would like to see if we can get that.
No. Actually, I showed you the explosions of these electron capture supernovae. We do those self-consistently. And we have also published neutron star masses in this case. And the neutron star masses are very roughly, the mass of this oxygen neon magnesium core. And the oxygen neon magnesium core develops a mass of the order of 1.35, 1.36 solar masses baryonic mass. And when you then calculate the gravitational mass, you get around 1.27 solar masses gravitational mass. You don't get less. If you want less mass in the neutron star, you would actually have to dump much, much more energy by neutrinos than we get in these self-consistent simulations, because energy deposition by neutrinos in the neutron star near surface layers would then expel a lot of material from the neutron star surface. But in that case, also the explosions would be much more energetic. Mm-hmm. Now, oxygen, neon, magnesium cores are not the cores providing the lowest neutron star masses. The lowest neutron star masses come actually from a certain regime of iron core progenitors. And now if you ask me, what is the mass then? I tell you that this iron core mass, or the mass of the neutron star, can reach about 1.3, maybe 1.28 solar masses, baryonic mass. And when you calculate the gravitational mass of that, you end up at about 1.2 solar masses. But below 1.2 solar masses, I have no viable model to present. I don't know how you should get neutron star masses below 1.2 solar masses.
So what's the mass of the progenitor that produce the lowest mass, you say?
This is typically in the mass regime around 10 solar masses, but that is there was a recent paper published by Umeda and Suva, and they used models from Umeda, who is a Japanese stellar evolution modeler. Yeah. Mm-hmm. But unfortunately, Yudai Suva exploded those models with his very approximative neutrino transport. So he gets neutron star masses which are certainly underestimated. So he claims in that paper, Suva and Umeda, he claims in that paper he can get neutron star masses as low as 1.17 solar masses. I question this. This is a consequence of this approximative treatment of neutrinos, which he has in these simulations. If we got the models from Umeda, we don't have their models. If we got those models from Umeda, we would probably end up with neutron star masses around 1.2 solar masses. The models provided to us from Stan Woosley actually don't form these low mass neutron stars quite as low as Umeda's models are. The point here is that stellar evolution modeling in this regime of low mass progenitors is extremely difficult. And it's therefore highly disputed, and there is no unambiguous stellar evolution model in that mass regime, because these stars undergo pulsations. And these pulsations depend on how stellar evolution modelers treat the convective burning. And whether they include overshooting, don't ask me, I'm not a stellar evolution modeler. I just remember a talk Stan Woosley gave at our institute back in 2016 or so, when all of us could still travel. He was here for a talk and he presented his models in this mass regime. And he said, what I get depends very much on the input, and in particular on my treatment of convection and semi-convection, or what he did.
Okay, but so 1.2 would be like the absolute minimum.
That is the minimum which I can tell you with good feelings as a lower mass limit at the moment from the best modeling we can do. That's of course based on the stellar models provided to us. I mean, if stellar modelers achieve to produce smaller cores at the onset of collapse, then it may lead to smaller neutron stars. Or if the neutron stars radiate neutrinos much more intensely than we currently find in our simulations, then this may actually lead to some extra mass loss on the surface of the neutron star. And when we speak about 1.2 compared to 1.17, we speak about 300th of a solar mass. And that is, of course, the difference which Yudai Suva's approximative neutrino transport gave, where there was more mass loss from the neutron star surface because of more energy deposition in the neutron star surface. So if we talk about these tiny details of a few hundredth of a solar mass, then maybe some change in the neutrino physics could provide lower neutron star masses. If you say you want a neutron star as low as 1 solar mass, then I tell you, no, not with the most extreme currently plausible modifications in the input physics, in the neutrino physics. I could imagine neutron stars becoming as low as 1 solar mass.
Okay, good. Thank you.
Yeah, you're welcome.
Yuri, please.
Yeah, thanks. Thanks for the talk. I had a question because I'm not sure I understood how the initial conditions are created. So
Are created.
yeah, so let's go into steps. So if I understood correctly, you take 1D models
Yes,
a little bit before, let's say, supposed collapse. You make
exactly.
it 3D, you perturb it a little bit, you let the convection
Yes.
go, and then
Yes.
you explode.
Yes, exactly. So we
Okay.
go back by 7 minutes, that means, or 5 minutes. So the stellar evolution people whom we collaborated with, I can name the person, Alex Heger
Yeah,
at
yeah.
Monash. Alex Heger provided stellar evolution models at -5 or -7 minutes before core collapse. And then we map these stars, we excise the center. That's the reason why you see on this plot, this white inner region. We take out the iron core and actually place a boundary condition, which we then use from the 1D models, which Alex Heger continued up to core collapse. So we contract this inner boundary according to his 1D models of stellar evolution. And then we simulate the volume in this oxygen shell, let's say between the silicon layer and the helium shell. We simulate the whole star in 3 dimensions. And that's over a period of 5 or 7 minutes. Yeah. And then we continue with the same code. We continue into the core collapse. Yeah.
So the second part of the question was, that's integrating, let's say, forward in time.
Yeah.
But if you take your let's say modified perturbed 3D configuration and you integrate it back in time, the star stays there. So
I'm not sure I understand exactly what you mean.
So my
Integrate back
question
in
is
time.
if that perturbation is going is let's say consistent in the sense that comes from a stable star, or if you
Yes.
integrate back in time, the star would explode, so to say. I don't know if I made clear.
No, I mean, let me try whether I have understood your question. This progenitor perturbation, or this, let me say, this large scale asymmetry and convection in this star is, of course, not leading to an explosion. There is no way how this convection could transfer enough energy to the overlying stellar material. Is that your question?
Let's say the question was if your initial condition would come from a star that would be stable, or if it was maybe oscillating too much and losing some matter.
Yeah.
Perturb it. So you have a situation -5 from explosion and integrate it forward in time. If you integrate that back in time, the star stays there and it's just oscillating, or is also losing mass? That was the question. I don't know if it's relevant or if you ever done it.
I'm not sure what you mean integrate back in time. I'm actually not sure. Do you mean we reverse the simulation and start with a perturbed state and just let the time axis in our 3D simulations go in the negative direction?
Yes.
Or yes?
Yes, yes.
Yeah, that's of course,
I mean, it's probably not very interesting, but just to check.
Yeah, well, you know, I mean, you know that this is there is a non-adiabatic effect here. I mean, we are not, we don't have adiabaticity. I don't think we could actually reverse the time axis perfectly because of the first law of thermodynamics. I mean, second law of thermodynamics.
Yeah.
Sorry, we could not do that. I mean, what you have, what your question is quite interesting, because I'm not sure that you're thinking in that direction, but there is stars, progenitor stars, which have been observed to obviously have some kind of eruptive phases prior to core collapse, prior to making supernovae. And these eruptive phases actually lead to a quite extreme mass loss from the stellar surface. And there is indeed a theoretical suggestion that this mass loss at the stellar surface, so millions of kilometers away from what I show you here on the slide, this mass loss is triggered by acoustic waves, which are created from turbulent convection in the interior of the star. And these waves then transport a little bit of energy outwards. And because the outer stellar layers are bound very loosely only, this can lead to mass loss episodes. But this theoretical conception has not been tested in detail by three-dimensional simulations. There is papers which argue against these arguments in the literature. Actually, my former student and postdoc Bernhard Müller has published such a paper. So there are concerns about this suggestion in the literature, but it's vividly discussed among stellar evolution modelers.
Okay, all right, thank you very much.
Thank you for your question.
Gloria, please.
Yeah, my question is actually related. So I'm interested in the progenitors and the massive ones, and in particular those which undergo this type of eruption that you mentioned, which is my understanding that the observed cases of an LBV type eruption prior to a supernova, the LBV has erupted about a year before the supernova. So it seems to me that this time scale is kind of long for the time scales in which the core becomes sufficiently unstable to collapse. But I mean, that's a different question from what I actually wanted to get to. So what I was trying to visualize is, at what stage in the evolution do you need these asymmetries to develop? In other words, do you need them in the silicon burning layer? Do you need them at a larger scale, physical scale? Or are you actually talking about the iron core, which is supposed to be convective? And I can't see easily how you get these asymmetries unless it's rotating very quickly. So that is my question.
Yeah, okay. So there's a lot of questions, actually. First of all, I have no information that the iron core is convective, because the iron core doesn't burn anymore. There is no energy release. But you're right, the silicon layer is convective. Right. What we have looked into is the oxygen layer. And the relevant time for us is, of course, the situation at the onset of collapse. And if I could actually just utter a wish to a nice, in a nice quiz or so, which then would let me win, I would say we would like to simulate the whole oxygen burning phase and the whole silicon burning phase in 3 dimensions. And we are not able to do that. We are not even able, in some cases, to run the silicon burning phase in 3D, because there is additional physics needed, which we would have to implement in the code, like neutrino and nuclear processes, which are not, which lead to neutron-rich material, which are very complicated nuclear networks, QSE treatments, which also require quite some computer time in 1D models. So we are not able at the moment to treat the silicon layer consistently. What is happening here is that the perturbed oxygen layer is falling in, and then at about 200, 300 milliseconds after bounce, it reaches a shock, and it helps pushing these post-shock instabilities. And there was another question is, you asked me how these start, or I don't know how whether this was a question, but you mentioned something like this starts, the convection actually starts from seeds. We have to actually seed this convection in 3D, but the seeds are natural to be expected, because at some level this medium will be noisy. And actually, when we then compare at the end of the second 7-minute simulation, compare the convective oxygen velocities here, they are pretty much compatible with the velocities predicted by the mixing length treatment of the 1D stellar evolution modeling. So I don't think that we end up here in a kind of a regime which is completely implausible with respect to the size and the asymmetries of the velocities which we see in the simulations.
But for example, if your oxygen layer were not chemically homogeneous, assume that you had a ring of different chemical composition in the oxygen layer.
That's what we had in this model here. That's what we had in this model. Okay. That model was a model which had a ring of neon in the oxygen layer. Yes.
So it had, so during the stellar evolution phase, in the late phases, you had enhanced mixing, perhaps in the equatorial region.
this model actually created this from a non-rotating state. It was a non-rotating progenitor. We have no models here where we simulated these phenomena where rotation in the star was taken into account. This unburned neon ring was formed due to some convective processes during the stellar evolution. You need to go to the paper which we published, Yadav. We actually discussed the initial state of this model in detail. I'm not able at the moment, with my background knowledge of these Kepler simulations, which were done by Alex Heger, I'm not able to answer why this neon ring formed within the oxygen shell, but there was a stratification of different chemical composition. And during these 7 minutes of simulation, actually the neon layer was eaten up by this turbulent convective burning. So you can question whether this neon shell of an unburned neon shell within the oxygen layer was realistic or was an 1D artifact.
Thank you so much. This is very helpful.
You're welcome.
Diego?
No. Okay, so in like the last slide or two, you put the list of all the successful 3D supernova. So there's, I don't know, like 12, 15 successful models from like 6, 8 groups. But what I didn't quite...
In total, sorry, I interrupt you just because I don't know whether your question needs it. So there is in total, I would say now, adding the large suite of models from the Princeton group, which has simulated about 15 models, and then all the other, let's say about 30, about 30 successful 3D models.
So my question is, from these 30, is there one specific model that has been able to be successful in 2 different groups? Because each group has different code, different physics, different resolutions.
Yeah, that's a very, very good question. And unfortunately, these groups, many of these groups, with one exception, the Japanese group, the one in Fukuoka in Tokyo around particular Kei Kotake, all the other groups have chosen different progenitors, which had not been published. And I find this very annoying, to be honest. We were the first group putting out some progenitor models, some successful 3-dimensional explosion models in 2015. And some groups, except for this Japanese group, have just started with their own models. I exclude here the Oak Ridge group, which came out in the same year. So they just started from a different progenitor model. This we didn't investigate that model at that time, so they were parallel to us and did it independently. But later simulations by this group here around Caltech and LSU people, they use partially MESA models, or they use progenitor masses which were different from the ones we had explored. The Princeton group actually uses, again, completely different progenitors, and they have not published any massive progenitors which we had investigated before. They have used the 8.8 solar mass model from Nomoto and the 9 solar mass model, which we also investigated. And in that case, their simulations are significantly more energetic than ours, a factor of 2 more energetic. So there must be significant differences in details of the physics, but I'm not able to answer you where the details are. I can only say we have published all the ingredients in our code. We have several code papers, test papers. We participated also in several tests comparing our code with other groups. And we find agreement in the input if we define the same inputs with those other groups.
But like, do you think there could be some plans in the future of like choosing one model and all these groups trying to get a successful explosion?
Yeah, that's a good point. That's a good point. This may happen. I think it will happen only once the main players in this field have actually harvested their simulations, because they want to first, of course, put out as many papers as possible with their results before they go to the next step, which is tedious comparisons.
Right.
And I'm not hopeful that this will happen very quickly. There's also some very unpleasant, let me say, competition and rivalry feelings in this field. I'm not sure that these collaborations will easily involve a lot of groups. On the technical side, there is one problem. The technical side is that three-dimensional simulations are not easy to run. Yeah. If we do such a comparative project, we would have to apply here for computer time, which of course needs proposal writing, which is always unpleasant, as you can imagine, and proposal reporting, which is even more unpleasant. And the question, of course, also is that whether a project which is just meant to provide computer time for a comparative analysis of different three-dimensional simulations finds support by the referee. You have to make a case. And so there is, of course, this difficulty in the let me say, in the setup of this field. Oak Ridge, for example, hasn't produced any three-dimensional model for years. I don't know whether the Chimera code, which they used in 2015, whether this Chimera code is still used in that group, or whether they are in the phase of producing a new code, developing a new code. The Tokyo Fukuoka group is probably easy to handle. If I ask Kei, let's do a comparison, he would probably say immediately, yes, why not? But it's very difficult to get this done. It's people may even point to a code comparison in 1D. There is a paper led by Evan O'Connor and my, at that time, student Robert Bollig. And there is all the other groups you see here have actually joined this comparative project, the Princeton group and also the Oak Ridge group, but the Oak Ridge group didn't use the Chimera code, which they apply in 1D. They used Agile Bolstran, which is a pure 1D code. And Princeton actually used the 1D version of their code, and there is some differences when you look at the results. So I'm really not able to answer more. I can tell you only the status of this field.
Okay, thank you.
Yeah, you're welcome.
Felipe, again.
Hello. So I am interested on the whole of pre-supernova progenitors on the circumstellar material. Mm-hmm. So I wanted to know if these instabilities you show have some hole on that, or what would be the main mechanisms of ejecting material from the progenitor before collapse.
Okay. I now refer to the main person doing or having put out this suggestion. The idea is that stars, as I show you here in their cores, in the convective oxygen layer, for example, they have extremely violent convection due to these bubbles I showed you. How this develops over a period of the full oxygen burning phase, I don't know, but you can still imagine that this layer is radially extended and convection will adopt some low mode pattern, as it usually does when it gets the volume. It fills the volume with the lowest modes, which you can fit into this volume. And if convection has these velocities as mixing length predicts, and we find here in this in this three-dimensional simulation, then at the surface of this convectively burning layer, you create also perturbations. You see them here in this plot. This is actually the velocity, and you see that you have radial velocity perturbations. And these velocity perturbations create acoustic waves, create waves which propagate outwards. And these waves transport energy. And they do that over the long period of oxygen burning, for example, several days or so. These waves transport energy towards the surface layer of the star. And therefore, in the surface layer, there is energy deposition because these waves run down a steep density gradient and they convert into shocks in the surface of the star. And these shocks then lead to mass ejection. And that has been put forward by Jim Fuller. He's in Berkeley, I think, or at Caltech or Berkeley now. And he has put forward this model or this suggestion, this theory to explain these mass loss episodes, which have been seen in some progenitors prior to core collapse. Yeah.
So how would you call this ejection of material? Because I read some authors that would call them like strong and steady wind or outbursts. How would you call them?
I would say this is probably eruptive because this is mass ejection which would happen from waves which steepen into shocks. And this probably is episodic and is probably also more violent than a steady state wind, which is subsonic. Shock waves are supersonic, they create supersonic outflow, and these waves are actually carrying packages of energy which are maybe pretty large or pretty big. This energy is not the same size as energy deposition as the energy deposition driving a wind. So I would probably expect that this should happen in eruptive and pretty violent phases, maybe even episodic phases.
Okay, thank you.
You're welcome.
And finally, Enrique, please.
Hi, thank you. Very nice talk, Thomas. Very grateful. I'm also really happy that you even took some time to talk about a couple of things that were very interesting, like SASIs and also the progenitor model. And regarding that last point, so we've learned in the last maybe decade or a couple of decades that the progenitors, being massive as they are, you will have most likely a companion star. So that should also affect the 3D models. And one of the things that you didn't talk too much about is, well, a couple of things: rotation and magnetic fields. And perhaps magnetic fields will be very important as well here. The configuration that you have might affect also the direction in which oscillations or whatever going on will occur. There's jets, there's jittering jets and all these things. And I guess what you need is, in a sense, to break the spherical geometry and make a hole through at least one point of the core, and that should suffice to make a successful explosion. Right? So you just need one direction in which you are successful, and that's
this is well, yes, that's right. I mean, that is what happens here when you see this model exploding. Actually, it explodes most strongly in the direction where this density in the progenitor, which is perturbed in the way you see here, where this density has, let me say, has a lower value. And that favors the shock expansion in this direction, where the explosion then becomes strongest. Yeah.
Okay, so how would magnetic fields be important here?
So yes, okay, this is a very difficult question. In particular, as you already pointed out, and your comment is certainly viable, if we take into account magnetic fields, we would also probably need to have the initial conditions, right? Because the magnetic field evolution will depend on the initial state of the magnetic fields. That is not in reach at the moment, because that would require to do something of that sort, including magnetic fields. I know two groups who are going in this direction. Maybe there is more groups around the globe. Maybe also Bernhard Müller at Monash is going in this direction. He has now a 3D version of his hydrocode. But I know that Miguel Aloy in Valencia, but also Fritz Röpke in Heidelberg, they want to use multi-D stellar evolution codes to study the magnetic fields in the progenitor star. Okay, so having said this, the question then is, what happens later with the magnetic fields? And with this artificially initially assumed magnetic fields, people have done some studies. And it turned out that if you take magnetic fields in non-rotating progenitors into account, magnetic fields don't do very much. They are amplified to some extent because of turbulence, but this amplification only, let me say, only in quotation marks, may push the onset of the explosion a little earlier. But we know a lot of effects which can move the onset of the explosion earlier. In the paper I mentioned here, this paper where we published this explosion, we actually show that including muons in the neutron star and neutrino-muon interactions also moves the explosion earlier. So this influence of the magnetic fields is certainly not dramatic. The situation changes completely when you take into account rotation and magnetic fields, because then you can actually amplify the magnetic fields in this protoneutron star or in the newly formed neutron star You can amplify these magnetic fields dramatically, and then magnetic fields also, if the rotation is rapid enough, can tap rotational energy. And that is the point I have put here down as last item on this slide of open questions. What is the relevance of stellar core rotation and magnetic field amplification in newborn neutron stars? And this is of relevance connected to the questions of magnetars, hypernovae, long duration gamma ray bursts, and potentially also superluminous supernovae. And my talk did not cover those phenomena, less or more exotic or rare, did not cover those at all. Magnetars are the most abundant one. There is speculations that about 10% of all core collapse supernovae are born as magnetars, or neutron stars are born as magnetars, but we have magnetars observed in supernova remnants, and these remnants have just the ordinary supernova properties. So I don't think that magnetars are connected to the onset and the energy delivered to the explosion. Magnetars probably form after the onset of the explosion, and the supernova is an ordinary core collapse supernova powered by neutrinos. It's different for hypernovae, long duration gamma ray bursts, superluminous supernovae. Those events are so extreme in energy, so asymmetric in their appearance, that this cannot be linked to the neutrino-driven mechanism.
Okay, thank you.
You're welcome.
Okay, well, I think that we can finish here. Then please turn on your camera. I just want to read a message from William because he had to run. Very nice talk, Thomas. Good to see you. I have to run. All best. Thank you very much.
Thank you for this great opportunity. Stay safe where you are. Avoid the third wave as much as you can. And it was a great pleasure for me. Thank you very much.
Thank you.
Thank you.
Thank you very much.
Bye.
Thanks very much.
Thank you. Thank you.
Bye.
Ciao, bye.
Bye-bye.
Bye.
Bye-bye.